Let's go ahead and start. This is Unit 1, and we'll start with section R.1. And we won't cover all these topics. We don't have time to cover all of them. Typically how these meetings go, we'll go for an hour and a half, where I'm going to be covering material and so forth. And then after that period of time, we'll stop the recording, and I'll leave the rest of the time available for any questions you have. So if you don't want your questions recorded and put on the internet, then they won't be. Section R.1 is sets in the real number line. And it says evaluate exponential expressions, square roots, and cube roots. Well, let me show you an exponential expression. This is the exponent. And that's read as 3 squared. And what that 2 means is it means we're going to multiply 3 times itself 2 times. Well, 3 times 3 is 9. Now, if we had, for example, 2, and this was squared, and the third power is cubed, but then you start going above that, and you say the fourth, fifth power, sixth power, so forth. So this is 2 to the 5th power. And again, that means we're going to multiply 2 times itself 5 times. So 2, 4, 8, 16, 32. Now we got a note on exponents. The exponent only affects what is to its immediate left, unless there is parentheses, and then it affects everything inside the parentheses. What we mean by that is if I had, for example, negative 2 squared. The exponent only affects what's to its immediate left, so it only affects the 2. The negative just carries down, and 2 squared becomes 2 times 2. Negative carries down, 2 times 2 is 4, so our answer is negative 4. Now compare that to negative 2 squared. The exponent only affects what's to its immediate left unless there's parentheses, and affects everything inside the parentheses. So here, since there's parentheses to its immediate left, what this means is we got negative 2 squared, so we'll have negative 2 times negative 2, which gives us a positive 4. Now, let me clear this off. And let's talk about square roots. Let's say I got square root of 9. This symbol right here is a radical. Specifically, this one's a square root. And to simplify a square root, we write the prime factorization of what's inside. 9 is 3 times 3. And with a square root, we're looking for a pair of somethings. Well, here we got a pair of 3's. So this pair of 3's is going to come out in front as a single 3. And that would be my answer. Now, if we had square root of 12, if I did prime factorization, glasses are killing me here. Well, 12 is 2 times 2 times 3. Remember I said we're looking for a pair of somethings. Here's a pair of 2's, so this pair of 2's is going to come out in front as a single 2. Now the 3 doesn't come out because we need a pair of them. There's only one of those. So that'd be our answer. Now that was a square root. You could have a cube root. Now this identifies a cube root. We got the radical symbol, and you got 3 in this slot right here. This slot is called your index. And that tells you how many you're looking for. So if I do the prime factorization of 27, that's 3 times 3 times 3. Now, since our index is 3, that means we're looking for a set of 3 of something. Well, here's 3 3's. So those 3 3's are going to come out in front as a single 3. Now consider if I had this. Now this is a square root, this is a cube root. Then it starts getting a 4th root, 5th root, 6th root, so that's how you pronounce those. If we did the prime factorization of 32, that's 5 2's. Now our index tells us how many we're looking for. So our index is 5, which means we're going to look for 5 of something. Well, here I got 5 2's, so this 5 2's going to come out in front as a single 2. I always try to make sure my microphone's at the same level as my nose. So if you ever see me doing that, you'll know why I'm doing that. When I have it down lower, you hear my breathing, and the video comes out worse. Not that it's that great a quality anyway. So if you see me do weird things like that, you know what I'm seeing if it maps up against my nose. Okay, now order of operations. This is what order do we perform the operations in? And there's a way to remember this. Please excuse my dear Aunt Sally. And actually, let me put my dear on one line, Aunt Sally on one line. We'll see why. The first letter in each tells us what we're to do first. So let me finish formatting those. The P. This says to do what is inside the parentheses. Now it might be brackets. It might even be little curly brackets. And get rid of absolute value. Now, notice what I say. I say do what's inside the parentheses. I don't say get rid of the parentheses. That might happen, but what we're doing specifically is we're doing what's inside of them. Now, for the absolute value, we are getting rid of the absolute value. The E is for exponents, so we do exponents next. My dear, that's multiply or divide as you encounter either one from left to right. Aunt Sally, we're going to add or subtract as you encounter either one from left to right. So if I had a problem, let me make up one. Let's see, 3 minus 1 squared plus 5 minus 2 squared to the third power. Please do what's inside the parentheses. Well, do this set of parentheses first. We got 3 minus 1, which gives us 2. So we got 2 squared, and everything else carries down. Still on the please part, doing what's inside this parentheses. Now notice here I dropped those parentheses because they weren't doing anything anymore. Within this parentheses, I still have to follow my order operations. Please excuse exponents. So I'm going to do this 2 squared first. Well, 2 squared is 4. Now I'm still doing what's inside the parentheses, which is 5 minus 4. That's the Aunt Sally, addition, subtraction. 5 minus 4 is 1. And those parentheses aren't doing anything anymore, so I can drop them. Okay, so no more parentheses. Please excuse exponents. Well, our first exponent's right here, 2 squared. 2 squared is 4. Still doing exponents. Here's our next exponent, 1 to the third. 1 times 1 times 1 is 1. And then our last thing, Aunt Sally, addition, subtraction. 4 plus 1 is 5. And that gives us our answer. Let's see what else. That's all exciting parts of section R.1. So let's go down to section R.2. Models, algebraic expressions, and properties of real numbers. Talks about algebraic models, identify terms and coefficients, apply properties, simplify algebraic expressions. Let's talk about some definitions first. We have a variable, which is a single letter. We have a term, which is a number times a variable, and I'll put an S on there because you can have more than one, or a variable times a variable, and I'll put an S on there to indicate you can have more than one. Examples of these: 5 would be a term. It's a number. 7x would be a term. It's a number times a variable. 2x squared would be a term. Now you might say, well, you didn't say anything about exponents. Well, 2x squared, let's think what that means. That means 2 times x times x. A number times variables. I didn't say they couldn't be the same variables. And when we're saying variables, we're talking about multiplication. Or a variable times a variable, that'd be like maybe x to the third. Because x to the third is x times x times x. Variable times variable. Those are all examples. Now we have coefficients. Your coefficient is the number in front of the variable in terms of multiplication. Example. The x to the third, back up here in our examples, the coefficient there is 1. The 2x squared, our coefficient is 2. The 7x, our coefficient is 7. And as weird as it seems, coefficient of 5 is 5. Now we're going to be taking a look at like terms here shortly. Like terms is where you have the same variables to the same power. And this is really not just like terms, but like items. You can think of it that way. And one last quick definition here. Degree is your largest power of x. In intermediate algebra, perhaps, if you took that class, you saw that it's a little bit more than that. If you had different variables, you'd have to add together your exponents. But for purposes of this class, that's going to be our best definition to work with. So, when it says apply the properties of real numbers, one we're going to specifically focus on is the distributive property. There's a lot of other properties you'll see in the homework, perhaps as many as 7, but this is the one that needs some explanation. If we have 3 times x plus 2. Now, anything right next to parentheses like this indicates multiplication. So when you got a number out in front, that's right next to parentheses, that indicates multiplication. So distributive property says we're going to take this number that's out in front. This is a single term, and we'll multiply it times x, and we'll multiply it times 2. So we got 3 times x, and we got 3 times 2. Well, 3 times x is 3x, and 3 times 2 is 6. So our answer would be 3x plus 6. Now, it doesn't have to be just a number. You could have like a negative 7x out in front, multiplied by x minus 3. Just as long as it's a single term, then we'll take this single term here and we'll multiply it times each item inside. Now, when I say each item, I'm talking about what's separated by pluses and minuses. You might say, well, what do you mean item? Don't you mean terms? Yes, in this case, I do mean terms. But you could have something looks like this later on in the course. And these aren't terms, but they are different items. What makes these separated is there's a plus in between them. So here I take the 3 and multiply times the square root of x and times the square root of y. So don't get thinking that this has to be terms. I try to lean away from that just to get people thinking just generally when you see a single item in front and you got 2 items inside, this is how you handle it. So we would take negative 7x times x and negative 7x times negative 3. Now when you got x times x, that's x squared. Thinking how exponents work. X squared means you got x times x. Negative 7 times negative 3 is 21, and then you have an x. And that'll be your answer. Now you're not limited to just 2 terms inside, but you really should just have 1 term out in front. When you have something that looks like this, where you got 2 terms, x plus 3 times x minus 5. When you have 2 terms out in front, that's when you have to do something different. You don't use the distributive property. Now the last item here says simplify algebraic expressions. Let me clear this off. Well, what in the world does simplify algebraic expressions mean? Simplify is probably the most generic instruction you'll run across in algebra. What it means, partially, is get rid of parentheses and combine like terms, combine numbers at any step. Though really I should say the combine like items. Now here, I'd multiply the 5 times x and 5 times negative 2. And I'd take the negative 1 times x and times 3. So we're going to have 5 times x. We'll have 5 times negative 2. We'll have negative 1 times x and negative 1 times 3. So that gives us 5x. 5 times negative 2 is negative 10. Negative 1 times x is negative 1x. Negative 1 times 3 is negative 3. Now think about your order of operations. Please do what's inside the parentheses. There's nothing to do inside the parentheses. Excuse. There's no exponents. My dear. Multiplication, division. Well, we just handled multiplication, didn't we? Now, Aunt Sally. Addition, subtraction. That's what we're going to focus on now. Combine like items, like terms in this case. Like terms where we have the same variable to the same power. So these are both x to the first power. So 5x minus 1x gives us 4x. When you're combining like terms, you add or subtract the numbers that are in front. 5 minus 1 is what gives us the 4, and then the x just remains. And we got negative 10, negative 3, which gives us negative 13. And that would be our answer. Let me show one more example of that. We have x squared minus 7x plus 2 minus 3x squared minus 2x minus 5. Well, we're still getting rid of the parentheses. But you might be saying, well, there's no numbers in front of them. Well, yeah, there is. Can't see them. They're invisible. But there's an invisible 1 here, and there's actually a 1 here also. So in this case, I'm going to take this 1, multiply it times x squared times negative 7x and times 2. Well, 1 times x squared is x squared. 1 times negative 7x is negative 7x. And 1 times 2 is 2. Mostly, if you have parentheses with no number or no negative in front of it, you just drop the parentheses. And here, a negative in front will flip the sign of everything inside. So that's what that accomplishes. It's the same as multiplying times negative 1. Negative 1 times 3x squared is negative 3x squared. Negative 1 times negative 2x is positive 2x. And negative 1 times negative 5 is a positive 5. Now to combine like terms. Like terms is the same variables, the same power. Here's an x squared and here's an x squared. So we're going to add or subtract the numbers in front. So we got 1 minus 3, which gives us negative 2x squared. Now here's an x and here's an x. Negative 7 plus 2 is negative 5, and then the x remains. And numbers. 2 plus 5 gives us 7. And that would be our answer. And that's the end of that, what we're going to cover in that section. So let's take a look at our R.3. I'm going to grab a drink here. By the way, we're going to expand that multiplication we just looked at when you get down to R.5, where we multiply polynomials together. Now this is talking about integer exponents in the scientific notation. So some basic properties we're going to take a look at. So we got x squared times x to the third. Now if your variables are the same, and you got x to a power times x to a power, you add your exponents. So that'd be x to the 2 plus 3 power, or x to the fifth. Now that one's not too hard to remember. If you forget that, x squared, that means x times x. X to the third means 3 x's. Well, going backwards, 1, 2, 3, 4, 5, we got 5 x's, that'd become x to the fifth. So again, that's a property that's pretty easy to derive. Now if we have x squared raised to the third power, if you got an exponent you're raising to another exponent, you multiply the exponents together. So this becomes x to the 2 times 3 power, which is x to the 6. Now again, if you don't remember this, it's not a huge deal. X squared to the third power. Well, the third power means I'm going to take x squared times x squared times x squared. 3 of them. Now each one of those x squared can get rewritten as x times x. So then I got 6 x's, so I got x to 6. And then you can see what happens when you got an exponent being raised to another exponent. Now, let me write this down. It should have this name. It doesn't, but it should. It should be called the distributive property of exponents. And it says if everything inside the parentheses is either multiplication or division, and you're raising the parentheses to a power, then you take everything inside to that power individually. So if everything inside the parentheses is either multiplication or division, you're raising parentheses to a power, then you take everything inside that power individually. What in the world do I mean by that? If I have x squared y to the third over z, all of it being raised to the fifth power. So if you everything inside parentheses either multiplication or division. Now we got x squared times y to the third divided by z. Everything is multiplication or division. And you're raising parentheses to a power, then you can take everything inside of that power individually. Well, we're raising everything to the fifth power, so I can take the x squared to the fifth power, the y to the third to the fifth power, and the z to the fifth power. We're talking what's separated by multiplication and division is what you take everything to the power. So we're going to have x squared to the fifth power. We'll have y to the third to the fifth power. And we'll have z to the fifth power. Now when you raise one exponent to another exponent, you multiply them together. So 2 times 5 is 10. So we're going to have x to the 10th. Y to the third raised to the 5th. 3 times 5 is 15. So we're going to have y to the 15th. And if you don't have a power here, and you raise it to a power, then that power just remains. So you'd have z to the 5th. It's equivalent to, if you don't have a power here, you got by default 1, and 1 times 5 is 5. Now compare that to this problem, which we'll see here in a little bit. A lot of people think, well, you can apply it here. You can take the x to the second power and the 3 to the second power. No, you can't, because everything inside your parentheses has to be multiplication and division. We have a addition in here. That's what causes us not to be able to do that. Here we have to rewrite this as x plus 3 times x plus 3, and then we'll have to do something different with that, which we'll see. Now this next, I'm going to write these steps, or this process down, but if you got x to a power over x to a power, like x to the 5th over x squared. Now I'll write this in terms of x's, but it applies to any variable. If you have x to a power over x to a power, then subtract the smaller exponent from the larger exponent, and you have x to that power where the larger exponent was located, and 1 in the other part of the fraction. Well, like this one here. I got x to a power over x to a power. If I subtract a smaller exponent from a larger one, 5 minus 2 is 3, we're going to have x to the third. So we're going to have x to the third where our larger exponent was. Our larger exponent was on top. And then we have a 1 in the other location. You never have a fraction that has blank on top or bottom. That's why you're always left the 1 if everything else disappears. Now x to the third over 1 is x to the third. So that'd be our answer. Now if I had x to the 6th over x to the 10th, let's apply that same idea here. Well, we got x to a power over x to a power, so we'd subtract a smaller exponent from a larger one. 10 minus 6 is 4. So we're going to have x to the 4th where our larger exponent was, which is on the bottom. And we have put a 1 as a placeholder on top. And that'd be our answer. Now you can have a mixture of different variables on these. So you may have to do this process for 2 or 3 times, depending upon how many variables. Negative exponents. Let's talk about how to handle those. We don't like negative exponents. I'll do this with an example. So whenever we have a negative exponent, we get rid of the negative exponent by taking the part that's the negative exponent opposite of where it's at in the fraction. For example, here we got x to negative 2. So we're going to move that up on top. Now when you move anything opposite of where it's at in the fraction, the sign of the exponent changes. So the x to negative 2 becomes x to positive 2. Now there's that 1 up there, and if you want to leave it there just to see it, then you can. Now there's blank on the bottom after we take that up on top. There's nothing left down there. Remember, you never want just blank, so you can put a 1 there. And 1 times x squared is x squared over 1 gives us x squared. Now you may start out with a negative exponent like this. Well, we don't want negative exponents, and we always do them the same way. We move them opposite of where they're at in a fraction. Well, in order to do that, you have to create a fraction. So I put the x to negative 5 over 1. Now we're going to move the part that with a negative exponent opposite where it's at in a fraction. So I'll take this x to negative 5th and move it down below. Remember, when you move anything opposite where it's at in a fraction, the sign of the exponent changes. So it becomes x to positive 5. And we never leave that blank, so you put a 1 there. Now there's a special case when you got a fraction to a negative power. Okay, so we have a fraction to a negative power. How you get rid of the negative power here is you flip the fraction, take a reciprocal of it. So the x over y becomes y over x, and then this becomes a positive 2. Now anytime you, remember what we talked about earlier, anytime whatever's inside of parentheses is either multiplied or divided, and you raise it into a power, you can take everything inside of that power. So we'll take the y to the second power and the x's second power. So that's going to give us y squared over x squared. And that's our answer. Okay, let me clear that off. Let's talk about the 0 power. Now, anything to the 0 power is always equal to 1. So x to the 0 is equal to 1. If I had 3 to the 0 power, it doesn't matter what it is. If you have the 0 power, the 0 in the exponent, that's always equal to 1. Okay. I'm not going to cover scientific notation. I think that's pretty straightforward in the book. Let's go down to R.4. Grab a drink here. Get talking, my throat dries out. And number 1 says evaluate nth roots. Well, we have done that already. But just to refresh your memory of what we were talking about. Nth roots is like the 4th root of 16. If I did a prime factorization of 16, I'd have 2 times 2 times 2 times 2. Now our index is the number that's in the slot right here. And that's how many we're looking for. So since there's a 4 there, that means we're looking for a set of 4 of something. Here's 4 2s, so those 4 2s are going to come out in front as a single 2. And since there's nothing left inside the radical disappears. Now, simplify expressions of the form a to the 1 over n power and a to the m over n power. We have to understand the relationship between a radical and that particular form. Let's say I'm looking at the cube root of 5 squared. So this is radical form. I can rewrite this as 5 to the 2/3 power. This is referred to as fractional power form. More commonly known as rational exponents. And how it works is whatever power is right here, that always goes up on top. And whatever number's in the slot, your index, always goes down below. Now, sometimes we want to go this direction, sometimes we want to go in reverse direction. Let's say I had 16 to the 1/4 power. And I want to simplify this. Well, fractional powers are hard to work with. You sometimes put them in that form so you can apply some properties of exponents. But at that point, then it becomes kind of tricky. I want to rewrite this in this manner. Go in the other direction. Whatever number's in your denominator right here in your power, that's what number goes in the slot here. That's your index. And then whatever number's up on top is what goes right here. So then this gives us the 4th root of 16, which we already saw back in this example is equal to 2. So we put it into radical form so we can simplify it. Now, This next topic is where we're trying to evaluate of the form a to the m over n power. Formatting's a little bit bad there, but let's talk about that. Let me clear this off. So I got 8 to the 2/3 power. And I want to simplify that. So simplifying a number to a fractional power, rational exponent, where the numerator is greater than 1. Step 1, put the numerator on the outside of a set of parentheses. Step 2, rewrite what is inside the parentheses in radical form. Step 3, simplify the radical. Step 4, simplify what is left. Put the numerator on the outside of a set of parentheses. Well, the number in the numerator is a 2. So what that means is we're going to take 8, and we'll put that 2 on the outside of a set of parentheses. Now remember what I said, we never leave blank here, so we'll put a 1 there. So your fraction never has a blank on top or bottom. It's always a 1 if everything disappears. Step 2, rewrite what is inside the parentheses in radical form. Well, that becomes the cube root of 8 to the 1st. Remember how that works. Whatever number's in the denominator here goes in your slot, that's your index, and whatever power's on top is what goes inside here. Step 3, simplify the radical. Well, 8 is 2 times 2 times 2. Now our index is 3, which means we're looking for a set of 3 of something. Well, here's 3 2's. So 3 2's and come out in front as a single 2. And then our last step is to simplify what's left. 2 squared is equal to 4. And that'd be our answer. Now, the next topic says simplify expressions with rational exponents. Let me clear this off. If I had 3 to the 1/2 power raised to the 2nd power. This is an example. Well, you think back to your properties that we talked about earlier. When you raise an exponent to another exponent, you multiply them together. So I'm going to have 1/2 times 2. And 1/2 times 2 gives us 1, so that'd give us 3 to the 1st, or 3. Now if I had 5 to the 1/3 times 5 to the 5/3, well, remember where we had x to the squared times x to the 3rd? X to a power times x to a power, you add the exponents. These are both 5. Well, since they're both 5 to a power, I'm going to add my exponents. So we're going to have 5 to the 1/3 plus 5/3. 1/3 plus 5/3 is 6/3. And 6 divided by 3 is 2. So that gives us 5 squared, which is 25. So the same properties that we saw before for exponents apply when they're fractions. Now sometimes they may start out in radical form, and you'll rewrite them temporarily in this form so you can do a little bit of simplifying, and then you may put them back into radical form. For example, this right here is the same as the 3rd root of 5 times the 3rd root of 5 to the 5th. And you can put it in this form so you can more easily work with that. Although we'll talk more about how to multiply those together. Simplifying radicals, we talked about that. Okay, so let's come down to polynomials and multiplication of radicals. Identify key elements of a polynomial. We talked about that. Your terms, coefficients. One thing we didn't talk about is standard form. So let's talk about that. Standard form of a polynomial is when the terms are arranged from largest power down to the smallest power. And even if it doesn't say to, you always put your polynomials in that form. Now, first thing it talks about is adding and subtracting polynomials. So let's talk about that. If we had x squared minus 5x to the third plus 2 plus x to the third minus 7x minus 9. This is adding polynomials. We kind of talked about this before, but these parentheses actually aren't doing anything, so I could drop them. So I got x squared minus 5x plus 2 plus x to the third minus 7x minus 9. Now, what we do at this point, after you get rid of the parentheses, combine like terms. Our largest power is x to the third, so I'll put it first. And then we got an x squared, so that goes next. Now our x's, we got negative 5x and negative 7x. That gives us negative 12x. And then we got numbers. We got 2 minus 9, which gives us negative 7. And that would be our answer. Now if I have x squared minus 3x minus 4 minus x squared plus 7x minus 1, this is subtracting polynomials. This first set of parentheses didn't do anything, so I drop it. I got x squared minus 3x minus 4. Remember what we said earlier. A negative out in front of your parentheses flips the sign of everything inside. So it's going to flip the sign of all those terms. So the x squared becomes a negative x squared. The 7x becomes a negative 7x. The negative 1 becomes a positive 1. Well, combine like terms. X squared minus x squared drops away. Negative 3x and negative 7x, negative 10x. And negative 4 plus 1 gives us negative 3. And that would be our answer. Let me clear that off. And we'll talk about multiplying polynomials. Well, I don't know why I have those glasses on there. I don't think I need them. Well, I'll leave them on. Remember, if you have a single term out in front and you have multiple terms inside, this is a distributive property. So we're going to take this 5x and multiply it times the x squared times the negative 7x and times the 1. So we got 5x times x squared. We got 5x times negative 7x. And you got 5x times 1. Now 5x times x squared is 5x to the third. 5 times negative 7 is negative 35. And x times x is x squared. And 5x times 1 gives us 5x. Okay, so that's just kind of what we've seen before. But if you have a problem that looks like this, x plus 3 times x minus 5. We no longer have a single term out in front. We got two terms here. Remember, terms are separated by pluses and minuses. So what we do is we take our first term, this x, we'll multiply it times each term in our second set of parentheses. Then we'll take our second term, the 3, and we'll multiply it times each term in our second set of parentheses. So I have x times x. I have x times negative 5. I have 3 times x. And I have 3 times negative 5. Now x times x is x squared. X times negative 5 is negative 5x. 3 times x is 3x. And 3 times negative 5 is negative 15. No matter where you are in algebra, you always combine together like terms if you can. So here, and it doesn't matter what step you're at also, negative 5x plus 3x is negative 2x, and then minus 15. There's probably one exception to that, and that's when you're factoring by grouping. Factoring by grouping and the key number method. Sometimes there you don't want to combine like terms because that's part of the process for the factoring. Now I'm not going to do this one, but I just want to show the setup. You might run across this one. You say, well, how in the world do you do this? Well, same way. We would take our first term here, this x, we'll multiply it times each term over here. Then you take your second term, the negative 1, and you multiply it times each term over here. So exact same setup. You take, actually, let me go ahead and set it up. X times x squared. You have x times negative 7x. You have x times 2. Then you take negative 1 times x squared. I'm doing my blue lines now. Take negative 1 times negative 7x. And negative 1 times 2. And since I've started down this road, let me go ahead and finish it. X times x squared is x to the third. X times negative 7x is negative 7x squared. X times 2 is 2x. Negative 1 times x squared is negative 1x squared, or negative x squared. Negative 1 times negative 7x is a positive 7x, and negative 1 times 2 is negative 2. Combine like terms. Negative 7x squared, negative 1x squared is negative 8x squared. 2x plus 7x is 9x. And then the minus 2 carries down. And that would be our answer. Now you may have heard of a method for multiplying polynomials together called FOIL. And our second example here, you could actually FOIL this. This would be first, outer, inner, and last. Now what that refers to is to figure out what to multiply together. The F stands for first. So multiply the first terms in each parentheses, x times x. The O stands for outer. We multiply the outer terms in each one. So that would be this x here times this negative 5. The I stands for inner. That means we multiply the inner ones together. That's a 3 times x. And then the last terms, we multiply the last terms in each set of parentheses. That's a 3 times negative 5. Now, FOIL works very well if you got 2 terms times 2 terms. You cannot FOIL this one, because this is 1 term times 3 terms. You cannot multiply this one using FOIL, because this is 2 terms and 3 terms. A lot of people get confused on when to use FOIL, and it's always when it's 2 terms times 2 terms. Now they got some special cases. Identify and simplify special cases. So let's talk about those. Let me clear this off. There's really only one special case we're going to look at. We've got x plus 3 squared. A lot of people think, well, you have to square the x and square the 3. You can't do that. Remember what I said should be called a distributive property of exponents? Says if everything inside is either multiplication or division, you can do that. We have an addition in here. So in this one, we have to rewrite this as x plus 3 times x plus 3. Now I'm going to use a line method I've been showing. So I'll take my first term here, multiply times the first term here, and times the second term. And I'll take my second term here and multiply times my first term here and the second term here. So following my red lines, x times x, our first terms. Follow my red lines, x times 3, those are our outer terms. Follow my blue lines, 3 times x, that's our inner terms. And 3 times 3, that's our last terms. So I got x times x is x squared, x times 3 is 3x, 3 times x is 3x, 3 times 3 is 9. And always combine like terms, 3x plus 3x gives us 6x plus 9. And that'd be your answer. And let me use that opportunity to grab a drink. Okay, let me clear that off. And they're talking about multiplying radical expressions involving multiple terms. I'm not even sure what that's referring to. Radical expressions aren't terms. It could be they're talking about having separate terms inside of radicals. So let's talk about multiplying radicals together. If we got square root of 5 times the square root of 5. Assuming your indexes are the same, then when you're multiplying radicals, what you do is you multiply what's underneath them. So you take 5 times 5, and then you put them underneath a single radical statement. So underneath a single square root. Now remember, with square roots, we're looking for pairs of something. So we don't actually want to multiply these together because we have a pair of 5s here. So a pair of 5s is going to come out in front as a single 5. And that would be our answer. Now if I had the cube root of 2 times the cube root of 4. Multiplying these together. Well, since the indexes are the same, I can multiply what's underneath, 2 times 4, and put them underneath a single radical statement. Now we don't actually want to multiply them together. We want to first see if we can simplify anything, and then we'd multiply them together. In this case, 4 I can rewrite as 2 times 2. Now our index is 3, which means we're looking for a set of 3 of something. Here's 3 2's. Those 3 2's are going to come out in front as a single 2. And that would be our answer. Now that's multiplying a single radical times a single radical. Let me clear that off. You could use some of the other techniques we just looked at. Notice we have a single radical in front, and here we have 2 radical expressions. Why I have 2 is because they're separated by pluses and minuses. Well, this is a distributive property. We're going to take square root of 2 times square root of 2, and square root of 2 times square root of 10. So we'll have square root of 2 times square root of 2, and we'll have square root of 2 times square root of 10. Now remember, when multiplying radicals together, you multiply what's underneath them. So we're going to have square root of 2 times 2. And here we'll have square root of 2 times 10. Now here we got a pair of 2's. So this pair of 2's is going to come out in front as a single 2. And over here, I don't want to bring anything out. Well, I can't yet. But I want to rewrite to 10. 10 is 2 times 5. Now here we got a pair of somethings. Here's a pair of 2's, so they're going to come out in front as a single 2. So we'll have 2 plus 2 square root of 5. Now you might be tempted to simplify that further, but you can't. You can't add 2 plus 2. It's because this is not actually a 2 here. This is a square root of 5. So 2 square root of 5 cannot be added to a single 2. Now where you can see that is if I multiply whatever together, and I end up with something like this. If the radicals are the same, see how these are both square root of 2's? If the radicals are the same, then you can add or subtract the numbers in front of them. 3 plus 5 is 8. So that gives us 8 square root of 2. So that's when you can combine them together. Now you may have problems look like this. We have 2 items here and 2 items here. Now the reason why I say 2 items is because they're separated by pluses and minuses. So we'd take the square root of x here times the square root of x here. We'd also multiply times the 5. And I'd take the negative 2 and multiply it times the square root of x and times the 5. So square root of x times square root of x. Square root of x times 5 minus 2 times square root of x minus 2 times 5. Now square root of x times square root of x, that's square root of x times x. Remember, if the index is the same, you multiply them together, you multiply what's underneath them. Square root of x times 5 is 5 square root of x minus 2 square root of x, and negative 2 times 5 is negative 10. Now remember, with square roots, we're looking for pairs of something. Here's a pair of x's, so they're going to come out as a single x. And over here we can add these radicals together. They're like items. If whatever follows the numbers are exactly the same, and you're adding or subtracting, then you can add or subtract the numbers, and whatever this is stays as is. 5 minus 2 is 3, and then the square root of x stays as is. And then I'll bring down to minus 10. And that's our answer. I say like items because it can be anything. It could be like terms. If you have 5x minus 2x, that gives you 3x. If you got 5 square root of x minus 2 square root of x, that's 3 square root of x. If you have 5, the absolute value of x, minus 2, the absolute value of x, that gives us 3 absolute value of x. So you're starting to see a pattern here. It doesn't matter what it is, just as long as they're alike, you can add or subtract them. If I have 5 and I had a smiley face here, and a smiley face here, well, same principle. We'd have 3 smiley faces. So it doesn't matter what it is, it's combining like items. Let me clear those off. And that's the end of that section. Now, next topic we're going to talk about is factoring. And that'll be a last topic. Rational expressions I never cover in this this particular session. They're kind of a lengthy topic. So factoring. Our first method of factoring is GCF. This is greatest common factor. Our second method we'll take a look at is grouping. And this is when you have 4 or more terms. Our third method we'll take a look at is one called PSD, and that's when it's of the form x squared plus bx plus c. We'll talk more about that. Our fourth method we'll talk about is key number, and that's when you got the form ax squared plus bx plus c. Our fifth is dots. This stands for difference of 2 squares. This is when you got 2 terms with a minus between them. 6-1 is a difference of 2 cubes. And this is when you got 2 terms with a minus between them. And our 7th one is the sum of 2 cubes. This is when you got 2 terms with a plus between them. So, let's say we have 7x minus 14. Our first method, GCF. When you have numbers Now we got two terms here. That's important. They're two different terms. When you have numbers, you look for the largest number divides into both those. We got 7 and 14, so our largest number divides in both those is 7. Now factor means to write as a product, but how we accomplish it is by dividing. So I take my first number here, 7 divided by 7 gives us 1, and the x remains, minus 14 divided by 7 is 2. And you never have 1s there for your coefficient, so that drops. And our answer is 7 times x minus 2. Now let's take a look at this problem. Same concept, the GCF. If I look at the numbers, I got 8 and 12. The largest number divides into both of those is 4. I'm going to bring a 4 out. Now when you have x to a power and x to a power, you want to bring out the most x's you can, but you can't bring out 3 x's if this one only has 2. So it's always one of the smallest exponents. So we'll bring out 2 x's. Now 8 divided by 4 is 2. Now I always tell people to visualize this. We start out, we got 3 x's sitting up on the table. Somebody comes and takes 2 of your x's away. How many x's do you have left? Well, we have 1 x. Plus 12 divided by 4 is 3. We had 2 x's and we took both those away, so there's no x's left. So this would be our answer. Now if I had negative 7x minus 49, I won't write down this note, but what it says is when you're doing GCF, if your first term is negative, you always factor out a negative no matter what. Well, here our first term is negative, so I know I'll bring a negative out. Now our largest number divides into both 7 and 49 is 7, so factor out a negative 7. Now remember, factor means to divide out, so negative 7 divided by negative 7 gives us a positive 1 with an x. Negative 49 divided by negative 7 gives us a positive 7, which then gives us negative 7 times x plus 7. And that's our answer. Let's take a look at grouping. Ignore what you're seeing there. I'm making up a problem. Some of these I can make up in my head, others I have to actually write out. Okay, AB minus 7ax plus 2bx minus 14x squared. Okay. Now if I look at this, I got 4 terms, and I'm looking at all 4 terms. I notice they don't have a GCF in common. That's always your first method you look at. You look for GCF. So since there is no GCF, I go down my list. My next one says if you got 4 or more terms, you try grouping. Well, we got 4 more terms. Now with grouping, what we do is we group first 2 terms together and group last 2 terms together. Now you won't put lines underneath them like that or mentally group them. Now visualize covering up this second group, and you only look at the first group, and you ask yourself what the GCF is. Well, that'd be A. And if I factor that out, that gives me B minus 7x. Now our second group here, I look at it, and I notice they are both divisible by 2, and they both have an x. So I factor out a 2x. And the 2's gone, the x is gone, so that's B minus 14 divided by 2 is 7. I had 2 x's here, I took 1 away, so that leaves me a single x. Now our goal with grouping is we want to get this parentheses same as this parentheses, which they are. So I'll factor out a b minus 7x. Now to see what goes in your second set of parentheses, you can come up here and cross out the b minus 7x's. And what isn't crossed out is what goes right here, which would be a plus 2x. And that would be our answer. Grab a drink. And I'm going to clear that off. Now next method is a PSD. Let's see. Let's say we got x squared plus 10x minus 24. Let's see, GCF, there isn't any. We've got 3 terms that don't have anything in common. Grouping doesn't fit because grouping is when you have 4 or more terms. We just have 3 terms here. Now the form I'm specifically looking for with a PSD is I'm looking for an x squared, x, no x, and there's no number in front of our x squared. Now notice how I'm not really emphasizing what in the world b and c are. That's not important for this form. We just got an x squared, x, no x, and there's no number in front of our x squared. So x squared, x, no number in front of our x squared. Now at the PSD, we take the number at the end, ignoring signs, and we're going to create 3 columns, a P column, an S column, and a D column. Now the P stands for product, so we're going to write down all products give us 24. We got 1 times 24, 2 times 12, 3 times 8, 4 times 6. Now the S stands for sum. We're going to add these 2 numbers together. 1 plus 24 is 25. 2 plus 12 is 14. 3 plus 8 is 11. 4 plus 6 is 10. The D stands for difference. We're going to subtract the smaller from larger. 24 minus 1 is 23. 12 minus 2 is 10. 8 minus 3 is 5. 6 minus 4 is 2. Now, a number we're looking for is a number in our middle term, 10. We got 2 10s. I hadn't planned this coming out this way, but occasionally you have that. Until you get comfortable with the signs, what you do is you try one and see if it works. If it doesn't work, it's the other one. And I'll talk about how can you tell it worked in just a second. There is a shortcut. If your last term is a positive, it'll always be in the S column. If your last term is a negative, it'll always be in the difference column. Since our last term is a negative, I know the 10 I'm going to use is this one right here, which means I use 2 and 12. Now, last thing we have to determine is what our sign is going to be. And let me type these out. So note on the signs for PSD / key number. It works for both of them. The larger number in the P column that we are using is always the same sign as the middle term. So a large number in P column we're using is always the same sign as the middle term. Now, if the number circles in the S column, it's S for same signs, both positive, both negative. If the number is circled in the D column, it's D for different signs. It means one's positive, one's negative. Okay. Large number we're using. We're using 2 and 12, so our larger number is a 12. It will always be the same sign as the middle term. Middle term is positive, so this is going to be a positive. Now a number I circled in the difference column. D for different signs. So since this one is positive, then this one is negative. They have to be different signs. How can I tell if that worked? Well, if you multiply this together, it should give you your original problem. That's why if you chose the wrong 10 and you multiplied it back together, it would not give you the original polynomial. Now let's take a look at another one of those. Let's see, x squared minus 32x plus 60. Yeah. Okay, GCF, there isn't any. Groupings, 4 or more terms, no. PSD is when you have x squared, x, no x, and there's no number in front of your x squared. Now remember with PSD, we take our number at the end, ignoring signs, so work with 60. And we'll have our 3 columns. We'll write down all products give us 60. We got 1 times 60, 2 times 30, 3 times 20, 4 times 15, 5 times 12, and 6 times 10. Add these together. 1 plus 60 is 61. 2 plus 30 is 32. 3 plus 20 is 23. 4 plus 15 is 19. 5 plus 12 is 17. 6 plus 10 is 16. Subtract smaller from larger. 60 minus 1 is 59. 30 minus 2 is 28. 20 minus 3 is 17. 15 minus 4 is 11. 12 minus 5 is 7. 10 minus 6 is 4. We could have, if you remembered the trick about to sign it here at the end, could have just wrote down the S column. We didn't need the difference column. Number we're looking for is always a number in our middle term, 32, which is right here, which means we use 2 and 30. Now remember our note on our signs. The larger number that we're using 2 and 30, so larger is a 30, will always be the same sign as the middle term, which in this problem is a negative. Number I circled in the S column, S for same sign, so if this one's negative, then this one has to be negative. And that'd be your answer. Now that's a PSD. So let's take a look at a key number. Let's see, 5x minus 1, 2x minus 3. So we've got 10x squared minus 17x plus 3. Double check that. Okay, 15x minus 2 plus 3. Start going down to my list. GCF? No. Grouping is 4 more terms? No. PSD is close, except for there's a number in front of the x squared. Now, specifically with the key number, what we're looking for is we're looking for an x squared, x, no x, and there's a number in front of your x squared. X squared, x, no x, number in front of our x squared. This is key number. So we're going to take the number at the beginning times the number at the end, ignoring signs. What do I mean by that? Number at the beginning. Well, that's our coefficient on the x squared. And then number at the end. That's our constant term. Now, if any of these were negative, you'd still ignore the signs. Although if the first term here is negative, your GCF would have forced you to factor it out to begin with. But if this had been a negative 3, we still would have went with positive 3. If you're wondering what's A and C stand for, well, A is whatever's in front of your x squared, and C is your number at the end. It just matches this form. Now we're still going to build a PSD table. We're just going to do something a little bit different with it. So we write down all products give us 30. We got 1 times 30, 2 times 15, 3 times 10, and 5 times 6. Add those. 1 plus 30 is 31, 2 plus 15 is 17, 3 plus 10 is 13, 5 plus 6 is 11. Subtract them, smaller from larger. Sorry, I was thinking what number I was looking for. 17. Okay, it's right there. 30 minus 1 is 29. 15 minus 2 is 13. 10 minus 3 is 7. 6 minus 5 is 1. Now we're still looking for a number in our middle term, the 17, which is right here. So we're going to use 2 and 15. I could have used, again, the fact that this is a positive to look just in the S column. Now we're going to do something a little bit different with it this time, though. Before we just wrote down our answer. This time, the first term carries down, last term carries down. What we're going to do is we're going to rewrite our middle term using those two numbers, the 2 and 15. Now our notes and our signs still hold true. The larger number in a P column that we're using, which is 15, will always be same sign as the middle term, which in this example is negative. Now a number I circled in the S column means both signs will be the same, or both numbers will be the same sign, either positive or negative. So if the 15 was negative, the 2 will be negative. And then we have to use factoring by grouping. Now our first group has a 5 and an x in common, so I can factor that out. And that gives us 2x minus 3. The last group doesn't have any GCF, but notice my first term is negative. And we said for GCF, anytime your first term is negative, you always factor out a negative. So I factor out negative 1, and that gives us 2x minus 3. Now our goal is to get this parentheses same as this parentheses, which they are. So I'll factor out to 2x minus 3, and that gives us 5x minus 1. And that's our answer. Let me show another example of that. Let's see. I'll try to make up something a little bit different here. I think this should be in difference column. So we got 10x squared, 40 plus 39x minus 4. Okay. GCF. No, there's nothing in common. Grouping is 4 or more terms. This is 3 terms. PST is close, except there's a number in front of the x squared. Key number. We got an x squared, x, no x, and there's a number in front of your x squared. Well, key number, we take our number at the beginning times the number at the end, ignoring signs. So we got 10 times 4, which gives us 40. Write down all products give us 40. We got 1 times 40, 2 times 20, 4 times 10, 5 times 8. Add them. 1 plus 40 is 41, 2 plus 20 is 22, 4 plus 10 is 14, 5 plus 8 is 13. Subtract them. Smaller from larger. 40 minus 1 is 39, 20 minus 2 is 18, 10 minus 4 is 6, 8 minus 5 is 3. Number we're looking for is a number in our middle term, which is 39, which is right here, which means I'll use 1 and 40. Now our first term remains as is, our last term remains as is. But we're going to rewrite our middle term using these two numbers. The larger number in the P column we're using, which is a 40, will always be the same sign as the middle term, which is positive. We circled number in the difference column. D for different signs means one will be positive, one will be negative. Since the 40 was positive, then the 1 has to be negative. Now we're going to factor by grouping. First two terms have a GCF of 10x, and that gives us x plus 4. The last two terms have nothing in common, but my first term is negative. And anytime your first term is negative, you always factor out a negative. So factor out a negative 1, and that gives us x plus 4. Now our goal was to get these parentheses the same, which they are. So I'll factor out an x plus 4, and that gives us 10x minus 1. And that's our answer. Let me clear that off. And let's take a look at this problem. X squared minus 25. GCF. I got two terms. They have nothing in common, so no GCF. Grouping is 4 or more terms. This is 2 terms. That doesn't fit. PST and key number are both 3 terms. Well, this is 2 terms. Dots. Difference 2 squares. 2 terms with a minus between them. Well, 2 terms with a minus between them. That fits. Let's see if it works. With difference 2 squares, we try to rewrite it as something squared minus something else squared. And you ask yourself, what times itself gives you each individual piece? For example, the x squared, that's x times x. And 25 is 5 times 5. If you're able to rewrite it in this form, then you can use difference 2 squares. And it's a formula. We're going to label what's inside the first set of parentheses as F for first, and we'll label what's in the last set of parentheses as L for last. And our formula is F plus L times F minus L. Now everywhere there's an F, we'll put in X, and everywhere there's an L, we'll put in 5. So we got X plus 5 times X minus 5. And that's our answer. Now let's say I had x to the third minus 8. No GCF. Groupings 4 or more terms. That doesn't fit. PSD and key number are both 3 terms. That doesn't fit. Dots. 2 terms minus between it. That fits. But nothing times self would give you 8, so it would fail if we tried to use this. If we keep going down, there's one that says difference 2 cubes. And that's when you got two terms with a minus between them. You notice that's the same description as the difference 2 squares. If difference of 2 squares fails, then you come down and you try to rewrite it as something to the third power minus something else to the third power. The difference of 2 cubes. Now you ask yourself, what times itself 3 times gives us each individual piece? For example, the x to the third. That's x times x times x. The 8, 2 times 2 times 2. And that actually works. So I'll label what's inside the first set of parentheses as f for first. I'll label what's in the last set of parentheses as L for last. And this is just a formula. It's f minus L times f squared plus FL plus L squared. Now everywhere you have an f, you're going to plug in x. And everywhere you have an L, you'll plug in 2. So we got x minus 2, x squared plus x times 2 plus 2 squared. So that's x minus 2, x squared, x times 2 is 2x, and 2 squared is 4. And that would be our answer. Always looks like you can factor that ending part down further using PSD, but you can't. It'd have to be a pretty bizarre problem to allow you to go further. Let me erase this, and then we got one more example to look at. X to the third plus 27. It's no GCF. Grouping is 4 more terms. PSD and key number are both 3 terms. Dots doesn't work because this is not 2 terms of minus between it. There's a plus between it. Difference 2 cubes doesn't work for the same reason. Now look at sum of 2 cubes though. It says 2 terms with a plus between them. 2 terms with a plus between them. This tells us to try sum of 2 cubes. So I'm going to try to write this as something to the third power plus something else to the third power. And again, you ask yourself what times itself 3 times gives each individual piece. X times x times x gives us x to the third, and 3 times 3 times 3 gives us 27. Now I'm going to label what's inside the first set of parentheses as f for first. I'll label what's inside the last set of parentheses as L for last. And it's just a formula. F plus L times f squared minus FL plus L squared. So everywhere there's an F, I'll plug in x, and everywhere there's an L, I'll plug in 3. So I'm going to have x plus 3 times x squared minus x times 3 plus 3 squared. So that gives us x plus 3 times x squared minus x times 3 is 3x, and 3 squared gives us 9. And that would be our answer. And that's actually where we'll stop on the material. I won't go into 5R.7. You'll find that if you look in the unit here, and you look in Instructor YouTube supplemental videos, I put full lectures out here on all these different topics. So get down to here, the rational expressions we didn't cover. You can watch these and get a lot more explanation than you did in this brief presentation. I just kind of give you a quick overview here. If you're not sure about factoring trinomials, PSD and key number, you can watch this video and it'll go into a lot more depth. I'm going to go ahead and stop the video there, and then I'll answer any questions you have.